Okay, so in this lecture, we're going to be going over independent samples on the project workbook. Um, and this right here is the example workbook, so just be aware of that. Um, so if you go right here, we've got the independent reference workbook, and then we also have the independent example, and all of the rest of them. There's also paired, goodness of fit, and goodness of fit unequal. And just to make you aware, the reason why I have this set up the way it is, I have all of these workbooks set up in such a way that you are literally answering the same 18 questions for every single workbook or for every single test. And I have it broken down. So if you just follow this every single time, you'll be good to go. The only exception is goodness of fit is slightly different. Goodness of fit, the step for number 16, you're doing something slightly different because of the way that the data is set up. So I have another short lecture that goes over the assumptions, but we have the hypothesis, examples, the purposes, and the effect size right over here on the left-hand side. And then this right here, it says, what is it that you should use to test this? And so I've got that set up as well. So you can say, oh, what should I use to test these assumptions? You just come right over here and you're like, oh, this is what I should use. So just be aware of that. And then coming over here on the independent reference, we have all of the questions that you're answering, and then also what it is that you should look at in order to be able to find those answers. And some of this does get all the way back into Unit 1, like both of these charts are from Unit 1, so be aware of that. So let's go ahead and get into the example. So for this example, once again, we're using Hot Wheels again, and I really want to go back and edit these videos so that way you can see the super cool Hot Wheels stuff that we're doing. I'm going to show you really quick though. Let's see here. Um, Hot Wheels ID track. Okay, so this right here is look at the images. Um, this is the track for the Hot Wheels stuff that I have, and I have a motor that's attached to it that I modified, and the motor that I modified ensures that every single car that goes through, that the motor runs at exactly 3.8 amps, and all Hot Wheels motors are run on batteries. I actually changed it so that way it will run on from a plug, and then I test the amperage every single time to ensure that every single car is run the exact same way. And so we have a track that is extremely consistent. This right here, you're supposed to push it through with like this push thing, and I don't really like that because um, it's not consistent. And so it goes through a loop. It also goes over a jump, and then it goes around in a circle. And so the lap times and everything that we're looking at, uh, that's what it's doing. And I actually have some video of it, so I'll put some video up of it a little bit later of me testing all 30 some odd cars. And yeah, and I did it with my son, so it was a lot of fun. Um, Next, so let's take a look at this. So the independent example. What we do is we start right up at the top. The first thing that we need to do is we say, okay, what is the dependent variable? Well, before we even do that, let's go ahead and take a look at what it is that we're doing. Okay, so a track was set up to examine the difference in track time based on car design. Um, there we go. It is believed that there will be a difference in track time between Hot Wheels original cars, e.g., Hot Wheels has this whole line of cars so that they're not real cars, they're like concept cars, and they are made by Hot Wheels. They're not real cars, they're not like an Audi or anything like that. They're literally, the brand is Hot Wheels. And then they're made up cars, and comparing that to models of real cars. Can I be 95% confident that there is a difference in track times between Hot Wheels original cars and models of real cars? So I'm comparing the track times of Hot Wheels original cars and models of real cars. Like for instance, Audi, Lamborghini, um, Mustang, real cars with, real models. So the first thing that we need to do is say, what is the dependent variable? Well, the dependent variable is, the actual values. They are dependent on something. So we've got these values right over here. All these values are track times. So these are track times, and these track times are dependent on whether or not it's the Hot Wheels original cars or models of real cars. So what we're doing is we're going to come over here and we're going to say, what is the dependent variable? And the dependent variable is track time. Okay. Track time. And then what is the independent variable? In other words, what is it dependent on? And we're going to say it is dependent on the design of the car. Uh, so it's the Hot Wheels original cars versus the models of real cars. And if you look right in here, I even say a track was set up to examine the difference in track times based on car design. So design, it's either a Hot Wheels design or it is a design from a real car manufacturer. Okay. What type of data is the independent variable? So the independent variable, the car design, it's categorical or it is nominal. So I'm going to put nominal. Then what are you examining or comparing? Once again, go back to the independent reference and you're like, oh, what is it that I should be looking at to be able to answer these questions? Well, for this, you're looking under purpose, use of tests. So over on the left-hand side, you'll see, okay, we've got these purposes or this use of test for independent reference. So determine if there's difference between two independent groups, difference between interventions, difference in change scores. So what we're doing is independent groups. We've got two independent groups. So I'm just going to copy and paste this, Control C, and I'm going to go back to the example and I'm going to say, what are you comparing? And I'm going to go determine if there's difference between two independent groups of uh, let's do this, difference in uh, track times between the independent groups of Hot Wheels original cars, and it's literally Hot Wheels originals cars, and models of real cars. So you see, I just modified it to meet our example. Next, what is the tail of the test? Which once again, just look right at the independent reference. Um, and it says for the tail, different. If we're looking for a difference, it's two tails. If we think that the first variable is greater than the second variable, then it's right tail or upper tail. Then if we think that the first variable is less than the second, then it's left tail. So I'm going to go to independent example and look right up here. And I'm going to say a track was set up to examine the difference in track time. And is there anything in here that says that we believe that one is going to be greater than the other? No, all that we say is that there's going to be a difference. And so because we think that there's going to be a difference, we're going to say two tail. Okay. What type of test are you conducting? Well, the type of test that we're conducting is we're conducting in independent samples. And you might be wondering, why is it that I have you say, oh, we're conducting an independent samples test? The reason why is because on your exam and on your quizzes, I ask you, what type of test are you conducting? And you've got to be able to say, you've got to be able to identify the right kind of test to conduct. And because it meets the purposes for this test, this is the type of test that we're running. We have two independent samples, and we are comparing the means of two independent samples. Okay, next, what is the null and alternative hypothesis? Well, once again, for the independent reference, if you come right over here, I have examples of how to write the null and alternative hypothesis. This right here is a non-directional, and this right here is a directional. More specifically, this is when you expect the mean of sample one to be greater than the sample two. So what we need is we need this one right here, and I'm literally just going to copy and paste this. So this says right here, the mean of sample 1 is not equal to the mean of a sample 2. And so I'm going to put this right here, and then I'm going to do it again, press Alt Enter, and then so the alternative, or H sub 0, oops, I don't know why I did that. Okay, H sub 0, that's the null, and then this is the alternative, and it did it again. I don't know why it's doing that. H sub, this is driving me nuts. H sub 1, I really have no clue why it just keeps popping up like that. So we've got the null and the alternative hypothesis. So this is saying for the null hypothesis, there is no difference. And then for the alternative, there is a difference between the two means. Okay, what's the level of significance? This is something that you in the real world will often have to choose for yourself. But for this one right here, I say, can I be 95% confident that there is a difference in track time between Hot Wheels originals, so on and so forth? And so the level of confidence or level of significance is 0.05. Because if you're 95% confident, then the level of significance or the alpha level is 0.05. What is the test statistic? If you have the population standard deviation, you're going to use the z-score. But this is often actually referred to as independent samples t-test. So we're going to be using the t distribution and the t test statistic. So what's the degrees of freedom? Well, this is a little complicated. And it really shouldn't be complicated, but there's multiple answers to this. First of all, you come right over here and it says, okay, what's the degrees of freedom? And for the independent reference, and it says number of observations for both samples -2, unless the assumption of the homogeneity of variance is violated. If it's violated, then use the degrees of freedom from the data analysis tool. Okay, so this is what we're going to do is first thing that we're going to do is we are going to test the assumption of the homogeneity of variance. But before we do that, let's just back up and let's just start from the very beginning. We're going to run a series. So we're going to run a total of 4 different tests. This right here is the most involved test that we do. So just be aware that you're doing more work for this test than any other test. Okay, so you'll see right here, run 4 tests with the data analysis tool: descriptive statistics, t-test assuming equal, t-test assuming unequal, and f-test. No matter what, just run all 4. Okay, so we're going to first do data analysis, and then I'm going to do descriptive statistics, press OK, and then I'm going to give what's the input range, and I'm going to do delete, and I am going to highlight all of the data, and it's fine that these are all blank on this. It's fine. And then do labels in the first row because you did highlight the labels. Then the output range, I'm going to say, okay, I want the output range to start right here. And then I'm going to want summary statistics, confidence level for the mean. Remember, we want 95%. And so press OK. And then it's overriding stuff, which is fine. Okay, then I'm going to come down. So I've got all the descriptive statistics, so that's good. And then we are going to come down here and run the f-test. So data analysis. Now the f-test, what it does is it's checking for a violation, like I said, of homogeneity of variances. With homogeneity of variances, I've got a whole lecture on this as well. But essentially, the question is are you comparing apples to apples, or are you comparing apples to oranges? Are you comparing a sumo wrestler to a ballerina, or are you comparing 2 basketball players? Variances, if you've got variance one group that's has a really has data that's spread out really differently than the other group, then when you have the 2 tests right next to each other, they can or the 2 distributions right next to each other, they're hard to compare. So I'm going to put variable 1. I'm going to highlight variable 1 range. I'm going to go up to the top. Hold on. Okay, so highlight variable 1. And then I'm going to highlight variable 2. And let's see here. Once again, I like to start up at the top and then go down to the very bottom one right there. And then I do have labels with an alpha of 0.05. And then I'm going to say, okay, I want the output range. Click right here. And let's see here. Where do I want this? I want the output range. I think I have f-test as second. Yep. Right under f-test for 2 samples for variances. So I'm going to put that right there and press OK. So I did the f-test, and we'll come back to interpreting that later. And then scrolling down, the t-test assuming equal variances, data analysis, and I'm going to do t-test assuming equal variances. So I scrolled all the way down to the bottom, t-test, 2 samples assuming equal variances. Even if it did violate the f-test, just run it anyway. I just want you to run all 4 of them. So variable 1 range. Once again, I'm going to go up to the top. Variable 1 and variable 2. Once again, just go to the top. And then labels alpha of 0.05. Just leave this blank, hypothesize mean difference. Just leave that blank. And then output range, we're going to click right here. T-test assuming equal variances. And then press OK. And then last but not least, where is the one for unequal variances? I must not have it there. Okay. So we're going to do one more for unequal variances right here. So we're going to do home. Oh, sorry, data analysis. Assuming unequal variances, press OK. Variable 1 range. Once again, we got to do it all over again. Lots of fun. And then variable 2 range. And then labels are there, and then the output range. Like I said, I forgot to put the, I'll make sure to have it in there for you guys. Or actually, I think I already gave it to you. So if it's not there, I'm sorry. I thought I had it in there, but just put it down below that and press OK. So we've got, it really should say Control C. And then I should put unequal variance. And so we have multiple tests that we're dealing with, and let's start up at the top. Okay. First of all, this brings us back to the question of what is the degrees of freedom? Well, the degrees of freedom should be the number of observations minus 2, because there's 2 categories. So if you go up to descriptive statistics, you'll see we've got 74 and 38. And so if you add those together equals sum, then you just add those together. And then, so there's a total of 112 observations minus 2, that's 110. However, with independent samples, what you need to look at is the f-test. And this f-test, if this p-value, this right here, if this p-value is less than 0.05, that means that you have violated the assumption of the homogeneity of variances. And this is definitely less than 0.05. So I'm going to highlight this in red and say, this is an issue. We violated the assumption of the homogeneity of variances. So therefore, we need to be using the t-test assuming unequal variances. And you'll notice the degrees of freedom is not 110, it's 108. But if you come right up here, the degrees of freedom is 110. And so we need to put 108 for the degrees of freedom, and we are going to be reading everything from the t-test assuming unequal variances. So for the degrees of freedom, we're going to put 108. Okay. So degrees of freedom, 108. Okay. And then what are the critical values? the critical values, we're going to come down here. This is another reason why it's really important to have the right, remember we put an alpha of 0.05. And so for the critical values for t-test, assuming unequal variances, we've got the critical for a one-tail or the critical for a two-tail. And so the critical for a two-tail is 1.982. So it's plus or minus 1.982. So I'm going to copy this. And I mean, it's not nice, but just has it right there for you. So we're going to come right back over here and we're going to say, what are the critical values? Let's see here. And we're going to put, sometimes this works, sometimes this doesn't, plus or minus. Yeah, I didn't like that. So let's do plus or minus 1.982. And we'll just go with that. So plus or minus 1.982. And then are there any assumptions violated? Well, what are the assumptions? Good question. So we're going to go back to independent reference and we're going to look at the assumptions. And there are a total of 6 assumptions. Well, first of all, we already know, well, let's start at the top. One dependent variable that's measured at the continuous level. So looking at this, we have one dependent variable, which is track time, and it is continuous. So that one's good. Okay. One independent variable that consists of 2 categorical independent groups. Okay, remember what the independent variable is? It's the design of the car. Is it a Hot Wheels design or is it a model of the real car? And so it is, that's categorical, split up into 2 different groups, so that's good. Independence of observations, so that means that each one of these are independent of one another. These are all each individual values, and so they are all independent. So that one's fine as well. Okay. Next, no significant outliers in the 2 groups. So in order to do that, once again, you can look at this on the right-hand side to say, oh, what is it that I should be using? So we should be using a box and whisker plot. Okay. So what we're going to do is we're going to say, and by the way, I'm going to fix this. I'm going to say track time. I'm going to put Hot Wheels track time and then real car track time. Just to make it a little easier to follow along with. But I'm going to highlight all of this and I'm going to say insert. And I'm going to click box and whisker. And you'll notice, well, it did not like me there. Okay. There are definitely outliers. And so I'm going to zoom out a little bit. Okay, and I'm going to put it where I want it to be, which is right up here. So we've got these, this chart right here. And so this is, let's see here. Track times for Hot Wheels and real cars. Okay, and so we've got this information right here, and let's see here. I'm trying to show you this. There we go. So let's click on the Hot Wheels and track time, and then we're going to, if we double click on it, the chart design options will come up, and I'm going to add the data labels to the left. And then I'm also going to add a chart element. I'm going to add a legend on the bottom. And so you'll see the reason why I wanted, so I've got the Hot Wheels track time and real car track time. And so it's kind of hard to see this information. You can sometimes move this over. Let's see here. Well, let me move it over. Oh, you can just hover over it so you can see it. So what we're going to do now is we are actually going to what you should do is fill out all of this information for both of these, for the track times for the Hot Wheels and for the real cars. So I'm going to zoom out a little bit so that way you can see how to do this. Let's see here. Let's put this right here for Hot Wheels Originals, and then we'll put real cars. And so it says number of outliers above, and you'll notice, okay, we've got a total of 1, 2, 3, 4, 5, 6 is what it looks like. Now this can be a little deceiving. The reason why is because it shows us right here the this point right here, 3.53. This is the largest value that is not an outlier. And so it looks like there are 6 values that are above that, but what we really need to do is determine, there's a couple ways to do this, but if you sort this, sort largest to smallest, and just continue with the current selection, you'll be able to see, okay, how many values are there above that? Let's see here. How many values are there above that 3.63, 3.53? So we've got a total of 1, 2, 3, 4, 5, 6, 7, 8. So there's 8. And they're just kind of like overlapping, so you can't always see them. So it's better to actually look at them. There's also a formula that you can use, but the formula is a little cumbersome, so it's a lot easier to just sort these and count them. So 1, 2, 3, 4, 5, 6, 7, 8. And so what I'm going to do is I'm going to say there are a total of 8 outliers between 3.63 and 7.4. 3.63 and 7.4. Okay, so 8. So 8 outliers between 3.63 and 7.4. Okay. And then the max value that is not an outlier, like I said, is 3.53. And then Q3 is, I got to zoom in a little bit, or we can just hover over it, and it's going to say 2.6325, 2.6325, 2.6325. The median, we'll just hover over the median. The median right there is going to be, let's see here, let's zoom in a little bit. We might actually need to, 2.24 is the median. So median is 2.24. And then the mean is the next question. The mean is 2.56. 2.56. And you can see, the mean is much closer to Q3 than it is to the median. So if the mean is greater than the median, then you know that it is definitely skewed, positively skewed. Okay, and then you've got 2.0075 for Q1, 2.0075 for Q1, and then the 1.25 for the minimum value that is not an outlier. So a min value that is not an outlier, 1.25, is that what yeah, 1.25. And then you can do all the same things over here for 2.48, so on and so forth, and just record all of these with this being 3, once again, sort these to make sure. Let me show you once again. Let me sort these from largest to smallest. Sort largest to smallest. And once again, continue with the current selection because we only want that row. And you'll notice The largest value that is not an outlier is 3.07 right there. So let's find all the values that are above 3.07, and that is 1, 2, 3, 4. So there's 4 values that are greater than the 3.07. Okay, even though it just looks like 3, there are 4. So there's 4 values that are above that, and then once again go through the whole process of doing this all over again. And I'll update this. I just want to make the video shorter and not doing it a whole second time. Okay. And so I'm going to zoom out. And so the question that brings us back: are there any assumptions violated? Well, with that box and whisker, we determined that there are definitely significant outliers. So there's significant outliers. So I'm just gonna there's significant outliers. Is it normally distributed? Well, in order to determine if it's normally distributed, we're going to look at the skewness and kurtosis. The skewness, if the skewness is greater than 1 or less than -1, then it is skewed, positively or negatively skewed. And then if kurtosis is above 3 or below -3, then it is, if it's above 3, then it's leptokurtic. If it was below, then it's platykurtic. So this is definitely leptokurtic. And so both distributions are positively skewed and leptokurtic. And they also both have outliers. And they also violate the assumption of the homogeneity of variances. So in other words, we messed up all of this. So in short, there are ways to fix this. But when you fix stuff like this, it messes a lot of things up. And so we're just going to move forward without fixing it. And what we need to indicate is we are doing this, and um, we just need to be aware that the results are questionable, and are not able to really be trusted the way that we want to trust them, because they do violate several assumptions. So I'm going to come right back here, independent example, and I'm going to say right here, dun, 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 any assumptions violated. Let's see here, homogeneity of variances, um, multiple outliers, and then also uh, normal distribution are all violated, um, because of the violations. The results, um, the interpretation of the results are questionable or cannot be trusted. Okay, so just be aware of that. Like I said, there are ways to fix it, but we're just not going to mess with that right now. All right, next, what is the calculated value of the test statistic? This is going to actually be fairly easy. The reason why is because we just need to come down to the t-test for some unequal variances. And remember, we are doing the t statistic right here, 1.3869. So we're just going to copy this, Control C, and then we're going to come right up here to that. So I put it right there. What is the probability of observing the sample? Once again, we just have to copy and paste it. So we've got the two-tailed test. Remember, because we don't know if it is, oops. So what is the probability? There's a 16.8% chance of getting this value or more extreme with a two-tailed test, because we have a two-tailed test. And yeah, let's see here. What is the probability? And then, Sorry. What is the calculated value? I accidentally put the critical value, I think. Or no, did I put the calculated value? No, I did put the calculated value. The critical value, we already put that plus or minus 1.98. And so looking at this 1.38 compared to the plus or minus 1.98, because 1.38 is less extreme than the plus or minus 1.982, we failed to reject the null hypothesis. So we're going to put fail to reject the null hypothesis. And so what we're going to put is the calculated value of the test statistic determined by the data analysis tool for t-test of independent groups with unequal variances. Okay, that's all that I'm putting there. And then once again, I can just copy and paste this, Control C, and I'll just put this right there. I'm going to say the probability of getting this result yeah, result assuming there is no difference in speed between the two groups is about 16.8% or 0.1683. Okay, and you can literally copy and paste my work too and just modify it. Just make sure that you do modify it and update it for your work. So if you're like, oh, is there a better way to phrase it? Not really. The whole point is to be very succinct and direct. Okay, so fail to reject the null. Say because the calculated test statistic of 1.3869 is less extreme than plus or minus 1.982, we fail to reject the null hypothesis. Okay. And then what is the margin of error? Really straightforward. We've got two different margins of error. So we've got this margin of error right here. And then we've got this margin of error for sample 2. So we'll put margin of error for the Hot Wheels original cars is, and then I'm going to just copy this, Control C, and then I'll put this right here. For the models of real cars, then we'll delete that. Okay, is 0.21, indicating that based on the sample size, the actual mean we are 95% confident that the actual mean is we'll put the actual mean, what is 2.326 2.326 plus or minus 0.2176. Okay, so basically I just put in there, hey, I know what I'm talking about with margin of error, and I'm going to copy this margin of error for the models of indicating. So I'm going to copy this, Control C, and then put it right here. Indicating that based on the sample size, we are 95% confident that the actual mean for Hot Wheels original cars is, and let's find out what that is. What's the mean? 2.56. Plus or minus 0.2597. Okay, so for all intents and purposes, it looks like Hot Wheels cars tend to be a little bit slower than the models of real cars, but we don't have enough evidence to say that there really is a difference. And so that's what the whole point is. You know, so often we look at this stuff and we're like, oh, there is a difference, but then you've got to look at it a little bit further and say, yeah, but there's not enough evidence to really say that there's difference. Okay. And so the independent reference, let's come back here because we've got to do effect size now. So for effect size, what we need to do is the mean of sample 1 minus the mean of sample 2, the absolute value of that, divided by the pooled standard deviation. And so I'm going to show you how to do that. So we do equals the mean of sample 1 minus the mean of sample 2. And more specifically, we're going to put ABS for absolute value. Okay, divided by the pooled standard deviation. You're like, well, how do I get the pooled standard deviation? Do I have to calculate that? Really great question. So normally you would, but we're not going to have you do that. We're going to have you come down to the pooled variance under the t-test assuming equal variances. So you've got the pooled variance right here. And in order to get the pooled standard deviation, what we're going to do is do equals square root of the pooled variance. And now we've got the pooled standard deviation. Okay, so we've got the pooled standard deviation. And so we're going to do what's the effect size? We've got the absolute value of that of the difference score divided by the pooled standard deviation. So that gives us an effect size of 0.23. And for all intents and purposes, the only reason why you would ever calculate an effect size is if you actually have a significant result. So we really shouldn't even be calculating an effect size right now because we don't have a significant result. But we're going to come down here and we're going to look at the effect size, under independent reference, and we're going to see, okay, this is a 0.2, which means that it's a small effect size, which makes sense because we don't have a significant result. In other words, we're going to come right here and we're going to say, if we had a significant result, it would be a small effect size indicating that a large sample size would be needed to observe the difference, and the differ would not be extremely noticeable. Okay, so that's what effect size is. And then coming down here, what would you say about what you interpret? And this really should be, let's see here. Let's see, Merchant Center. So what was run? We're just saying, once again, this is just an overview, like a write-up at the very end. We ran an independent samples t-test was conducted. And then we're going to come up here and say, what was the purpose of the test? or what were you examining or comparing? So we're just going to Control C, and then we're going to come down here, Control V, to determine if there are differences in track times between the independent groups of Hot Wheels cars and the models of real cars. Okay. And then coming down here, what was the result? The results indicated that, oops, that we are not able to determine if there is a difference between the two groups based on the available information. Okay, so that's the results. What is the probability of this result? So coming right up here, what is the probability? If you do a good job writing up in here, you can just copy and paste this. What is the p-value of this result? So you put the probability. Yeah, so the probability of getting this result, assuming there's no difference between the two groups, is about 16% or 0.1683. So results, or more extreme. There we go. Assuming there is no difference. There we go. And then give insight into the possible factors. The sample size, a larger sample size could yield greater insight. But the present results may still basically, even if you get a larger insights, or sorry, a larger sample size, about differences, but the difference would not be extremely noticeable due and would have a small effect size. Okay, then coming down here, talk about the confidence interval. Once again, you can just come up here, confidence interval. We're just going to copy and paste both the information right here. Confidence interval, oops. So Control C. We are 95% confident that the actual mean track times for real model cars is, and then we're going to copy and paste the other one, margin of error. The reason why this is important is we're essentially looking at the two confidence intervals. We are 95% confident that the actual mean for Hot Wheels original cars is 2.56 plus or minus 0.2597. And so if you look at this, like you actually list these out. So let's actually look at these. So equals 2.326 plus 2.176, and then we'll do, or 0.2176, not 2 point. There we go. And then we'll do equals 2.326 minus 0.2176. So that's for, and really what I should have done, because we're always putting Hot Wheels cars first. So I should have put the Hot Wheels cars first right there. And then so we've got the real cars, Control X, Control V, and then we'll put Hot Wheels, and we will do equals 2.56 plus 0.2597, and then we'll do equals 2.56 minus 0.2597. Okay, and what we're looking at here is, do these two confidence intervals overlap? And you'll notice that they definitely do, because you've got this right here. This 2.3 falls somewhere right in the middle of this confidence interval, which we're 95% confident that the actual population mean for the Hot Wheels cars falls in this confidence interval, and we're 95% confident that the actual population mean for real model cars falls in this confidence interval, but it could be anywhere in there. So because these two confidence intervals overlap, essentially we're not able to tell that there's a difference. Okay, so the present results are not able to indicate that a difference exists and should not be used to indicate any kind of existing difference. Then you can also talk about effect size in there if you'd like. And then coming down here, last but not least, we're going to make a, we're actually going to make a frequency polygon. Make a frequency polygon. Polygon of the two variables. And so I'm going to make a pivot table. So I'm going to highlight these. Okay, control, let's see, insert, pivot table. So I've got those highlighted, and I'm going to say, where do I want this? And I'm going to come right down, let's see here. Put it, start just to the, we'll just start right here, make the frequency polygon. We'll do the whole process under here. So we've got the frequency polygon, and I want Hot Wheels track times, and there we go. And so what we've got to do is we've got to change the sum. We've got to change that to count. So I'm going to right click. I'm going to say summarize values by count. And then I'm going to, well, first what I'm going to do is I'm going to find the min and the max. So min and max for both. So you've got the, let's see here, min 1.25, 1.64, and then max is 7.4. And so what we've got there, we'll do min 1.25 to max of 7.5 for everything. Okay, so I'm going to come over here and I'm going to group this. Group 1.25 to 7.5, and I'm going to do it by 0.25. Okay, and so I've got all of these I'm going to copy this, Control C, and put it right here. And I'm going to do the exact same thing with the real cars. So sum of real cars, and then I'm going to bring this into rows, and then once again, you've got to change this, summarize values by count, and then I am going to group and do the exact same thing, 1.25 to 7.5. And it doesn't matter that there's nothing there, in those extreme areas, but we're going to group it by, once again, 0.25. And, we've got this information right here, and we're going to match it up and just put zeros where there's supposed to be zeros. And so we're going to, let's see here, Control C, 1.5, okay, and then 1.75, 2 to 2.25, and let's see here, 2.25 to 2.5, 3 to 3.25, 3.25. Ooh, so you'll notice right here, there is no 3.25. So we're going to Control X, and we'll do 3.25, Control X, and then 4 to 4.25. And I know that this is a little cumbersome, it's kind of a pain. But there's really, I'm sure, well, there is a better way to do this, but the problem is that the better way requires everyone to have a PC. So I'm doing it in such a way that I know everyone will be able to do it. Control C, I'm going to put this right there. Put 4, 4, and I'm going to put 0 and 0, and then I'm going to put zeros in there for all of the missing values. And it's going to be a little wonky, and the reason why is because of how messed up this data is. This data is actually really bad. So I'm actually kind of glad that I have this. And so this right here, you really should have, 5, what's it called? Let's do this, Control X. Let's do boom, boom, boom. So we should have 5 to 5.25, and then 5.25 to 5.5. And you see how bad this is. Let's see here. And then we've got to go all the way to 6. And then you get to do this all over again. With 6 to 6.25, 6.25 to 6.5, to 7, and let's just make sure, I think that is everything. So this right here, this is going to be all zeros. And you got to check to make sure that all of them are there. 1.5, 7.5, 3, and we were still missing one. It would have been so easy to miss that. So we've got 4.5 to 4.75, and we probably should have grouped these by 0.5, but it is what it is. So I'm going to, let's see here. Hot Wheels, and then real cars. And I'm going to, whoops. I don't know. Okay. Hot Wheels and real cars. And then we're going to do insert. So you'll kind of see how it is. So the 0.25 is really good because it shows this distribution right here. The other way that you could do it is with a relative distribution, which would actually work really well. I can show you how to do that really quick. But let's change this to 0.5. So let's do equals sum. See, and we're going to change this to like I would have done 0.5. Um, Data, text to column. Equals. Go. Control C, control home values, and bada bing, bada boom. Well, anyway, oh, I know what I did. That is exactly what I did. So this should just be 1. So that last one's just a little weird. So I got to add 1 to that last one. Paste values, and then do 3. And then Control C. Don't worry about. Basically, I just messed up, and I'm fixing this. And let's sort filter. There we go. Hot Wheels and real cars. And then if you wanted to, like I said, you could equals you could make these all relative. And if you make these all relative, it's actually going to, the graph is going to look a lot better. Equals divided by, and then put a $sign right there. Divided by, there we go, $sign. And let's bring this all the way down. and then Control C, put it right there, and it gives you Hot Wheels. Control C, Control V, oops, Control C, paste the values, and Control C, Control V. So this right here is relative, and this right here is the actual values. And so I'm going to show you the difference in the two. So I'm going to do insert, uh, and you'll notice when you do the relative, it actually shows you it's much more um, just accurate or representative of, or it doesn't mess up with the. Oh, that's unfortunate. I just lost all my work. Um, but it doesn't mess up with the sample size. And so that was just really unfortunate. Um, hopefully it saved it. Yep. Woohoo! It saved it. So when you look at the two of these, you'll notice that, okay, it looks like the orange is lower than the blue, or the real cars is lower than the Hot Wheels cars, but relatively speaking, the real cars are much more proportionately in the lower area than the Hot Wheels cars. But for all intents and purposes, there's not much of a difference between the two. The big deal is that there's a few Hot Wheels cars that are really slow, and that's what's really contributing to the Hot Wheels cars being slower than the real cars. And so you can actually put that in there if you put, the real cars. There's just a few outliers that are really messing everything up. So that's pretty much it for the independent samples, and hopefully I didn't confuse you too much at the very end. I should have just done it with a larger uh, with larger classes to begin with. And that would have made everyone's life a lot easier. And then doing a relative frequency polygon is definitely a lot better way to go than an actual frequency polygon. Frequency polygon. Cool. Uh, I think that's it.